There we go. All right. Today the plus C is going to matter. That's gonna become clear later. But today the plus C is gonna matter. So we're rocking and rolling in terms of progress on homeworks and whatnot. You all turned in 5.3 today, and I'm going to give you 5.4. 5.4 is a somewhat Excel-based assignment. It's a little bit structures, a little bit Excel, but that it'll become clear after the lecture today, kind of what the homework's all about. And one thing I'll tell you is that the homework, I think, is easier than what we're doing in class. So if you understand what we're doing in class, you'll be able to do the homework, no problem. Okay, so what we're going to do today is we're going to continue our discussion of shear and moment diagrams. Last time we did uniformly distributed loads, and we utilized this relationship and the conclusions that we made. And if you remember, we had talked about that scale of the polynomial sort of derivative and integral relationship. So when we were dealing with point loads, we had nothing on our loads, so we had constant shears and we had linear moments. And then when we said, okay, when we have uniformly distributed loads, we have constant loads, linear shear diagram, quadratic moment diagram. So for triangular loads, it goes a step further. Our load diagram is linear, so that means our shear diagram is quadratic, and our moment diagram is cubic. And there's going to be like a problem with triangular loads. There's going to be a little bit of a failure on the graphical approach, and the failure is this part right here, is where we integrate the shear diagram and to construct the moment diagram. Now, there's a couple of ways of going about this. We can break out the calculus approach and actually do the integrals. I'm going to try and avoid that, but I do want to show you a method where the calculus will work. But the main thing I want to illustrate to you, and the reason why I think Excel is going to be useful, is that the graphical approach is going to fail when integrating the shear diagram. See, before, when we were integrating the shear diagram, we either had rectangles or like triangular regions or trapezoids, stuff that we can compute the area of quite easily just with some basic formulas. But we're going to have a funky shear diagram, and so computing the area under that curve is going to be tough to do graphically. So hence why we're going to break out some other methods. Now, before we get into this problem, if you recall last time, I said, okay, before we do the shear diagram, the moment diagram, I want to handle some geometry, because I don't want the geometry. I'm going to close this. This is distracting me. All right. Before we handle the shear and moment diagram, we're going to attack some geometry first. And if you remember, the geometry problem was we have a shear diagram and we have the line going like this, and we needed to get the area of both of those triangles. And we just wanted to make sure that that was a comfortable thing to do. So here we've got a little bit more geometry. Now I'll go ahead and tell you this one ratchets it up a little bit in terms of difficulty. There's going to be some X's and alphabet soups floating around in this problem. But what I have here is a problem like this. So I have a triangular load, and what I've done is I've taken that triangular load that goes from 0 to 4 kips per foot over a distance of 35 feet. I just made these numbers up. And I'm going to be breaking out my secret weapon of structural engineering, which is the samurai sword or the lightsaber if you happen to be a sci-fi fan. And I'm going to be cutting right through that triangular load. And so if I cut a section and I look to the left, I need to be able to quantify this, okay? And I want to make sure that we're all comfortable with that. And instead of cutting a section, I don't know, 5 foot from this support or 10 foot from this support or 78.2 whatever from this support, I'm cutting it at a distance X from the support. And I'm doing that because I need to be able to write an equation that captures what the shears and moments are, okay? one of the things that, one of my tenets that I try and adhere to as a professor, particularly in a class like structural analysis, I know that this class at times seems like we're solving just a bunch of mathematical puzzles, and at times that can admittedly be what we're doing, but I always want to make sure that it's grounded in reality, okay? And I don't want to make you break out a bunch of algebra and calculus just because, just for the heck of it. There needs to be a reason for it. And there are reasons for this, I assure you, that will become clear as the semester progresses. So if I have you do a bunch of algebra and deal with a bunch of x's, there's a reason for it, trust me. Okay, so I want to attack this geometry problem. So let me go to this. I copied this here. Okay, so I have this triangular region here, okay, and ultimately I have, I would say, two goals, okay. I want to be able to quantify this term f. So remember how we take a triangular load and collapse it into a point load, right? I want to be able to quantify how much that load is, and I want to be able to quantify its moment arm. Now the moment arm is easy. If this is x, what is d? Say it again. No. From the big end. This is x. What is this? The 1/3 x. There you go. Okay. So ultimately what I'm going to try and do is basically say d equals something and f equals something. And they're both going to be in terms of x. So I propose that d is easy. Okay, let's just put this right here. I'll write it on the screen here in a second. D is x over 3. Okay? Now, if d is x over 3, let's write that here. I don't know why I put that on the board, but what have you. D is x over 3. What about f? F is the area of this triangle, which is 1/2 of base times height. And I don't know what the height is yet. We're going to figure that out. But I propose that the area of that triangle is 1/2 base times height. Is that fair? I don't think that's mysterious, okay? But I like keeping things simple whenever possible, and I would like to deal in a single variable, okay? So what I'm trying to figure out in this problem now is what is h, okay? And this is where the geometry part comes into play. So how do I determine what h is? I propose that the easiest way is to use similar triangles. In other words, I propose that 4 is to 35 as h is to x. Now, how did I get that? 4 is to 35 as whatever this h is to x. Does that make sense? I'll do that again. 4 is to 35 as h is to x. So therefore, h is just 4x over 35. Now, if I were to graph this equation, like y equals 4x over 35, what would it look like? It would be a line, right? What would be the intercept of that line? Zero comma mx plus b. If this was y equals mx plus b, what's b? 0, right? So if I were to graph this, wouldn't it look like this? It'd go kind of like that, right? This would be 0 comma 0. And if I put in x equals 35, What's the y distance? 4. Doesn't that match this red line right here? 0, 0, 35, 4. Isn't that just the equation of this line? So would you agree with me that this represents the height of that triangle? Make sense? So, therefore, if f is 1/2 xh, I can say 1/2 x 4x over 35, which is what? 2x squared over 35. You see what I did? The 4 and the 2 cancel, and the x times x gives you x squared. So now I've got the force and the moment arm in terms of x. Is that okay? Again, this is just a geometry problem off to the side. Has nothing to do with the actual shear and moment. Well, obviously has something to do with the shear and moment calculations we're about to do, but I just want to do that part off to the side. I don't want this to get in the way of the actual concept, okay? Does this make sense? Okay. Any questions? One other thing I will mention, note, because I think this is kind of nifty. I propose that, okay, height is 4x over 35, right? That tells you the height of the triangle as a function of x. Now, the load is going downward, right? I propose that if you wanted to write a function for the load, it would just be that. Because at any point x along the span, that's the load. It's just negative because the load's going down. Does that make sense? If that concept makes sense, then that concept will help me explain why plus c matters. You remember that. Plus c matters. I might appreciate it. You do not have to get me a shirt. But plus c matters. Okay, any questions? All right, if there are no questions, let's look at our target problem for the day. So here is our target problem. So we are going to draw the shear and moment diagram for this beam. Okay? Now, let's take a look at the beam. The beam is 30 foot long, and it has a linearly increasing load, a triangular load, from 0 to 2 kips per foot. I did not give you the reactions, okay? We're going to solve for the reactions and do it right, okay? Now, so that I understand, we can take this triangular load and collapse it into a single point load. What is the magnitude of that point load? 30 kips, because it's 1/2, 30 feet, 2 kips per foot, which is 30 kips. And what, so that we're clear, is that distance? 20. All right. So if I sum moments a day, I have 30 times 20 and by times 30. I get that, right? I'm hoping this part's simple, right? So therefore, I get that. Is that fair? I know I did that real quick, but I mean, there's only one load on the beam, right? And so just to round everything out, we know that if we sum forces in the x direction, if we do that, we're going to get that AX is 0. And if we sum forces in the y direction, what are we going to get for AY? Say it again. 10. So this is 10 kips. This is 20 kips. What do you think? I'll give you a sec to catch up because I don't want this to be tough. So far, so good? Okay, so now I want to illustrate the problem, like why this is different. So all right, so if I try and draw the shear diagram, okay, here's going to be the problem, okay? I'm going to start at 0. And jump up 10. So this is 0, and this is 10. Now, how much load is acting on the beam from beginning to end? 2 kips, but the total amount? 30. It's a linearly increasing load of 2 kips per foot, which is but ultimately 30 kips. So here's what I know. I start at 10 kips. Something happens, and if I'm at 10, I go down 30. I'm going to be at negative 20, and then this reaction is going to bring me up to 0, right? So I know that ultimately this is going to be negative 20, and then this is going to bring me back up to 0. The problem is I don't know what it looks like in between, but what it looks like follows this little to a lot or a lot to a little pattern. See, the load is increasing across the span. So that means that the magnitude of the slope has to increase across the span on the shear diagram. And since the load is going down, the slope has to start like this, and it has to get negative. So the shear diagram is going to look like this. It's going to look something like that. This quadratic shear diagram. Okay, and then what's going to happen is I've got to integrate this, integrate that. Those two areas have to match. And then I have to draw the moment diagram. And the moment diagram's got to start at 0. It's got to do something kind of like that. Wherever this crosses, like that. And then it's got to do this and go back down to 0. But I have No idea what that value is, or the areas of this, or this distance right here. And I know that some of you are probably thinking, wait, isn't that just 20 feet? No, it's not. Because it's not where the centroid of the triangle is. It's where the shear function equals 0. And those aren't necessarily in the same spot. It's close, but it's not quite. So there's a lot going on here that I don't know, right? Make sense? Everybody with me so far? So I propose that in order to do this, our new goal should be this. Let the math do it for us. Let it do the heavy lifting. Now, I'm going to give you two approaches to do this problem and show you how they both work. Okay? Now, one of the things that I have kind of glossed over in this problem is, do you see something on the beam that we've never written before? What's up here? The coordinate system, I've got a y and x axis, right? Okay? Now, I'm just going to write something here on the board. I'll reference it later. But would you agree that at x equals 0, would you agree that would you agree with that? Make sense? Just keep that in the back of your head. Just keep that in the back of your head. Okay. So, I'm going to show you two ways of getting these shear and moment functions. I'm going to call this the algebra-based approach. Okay? The algebra-based approach is this. What we're going to do is we're going to take that samurai sword and that lightsaber, and we're going to cut a section. Okay? Now, let me scroll up a little bit so that you see what I'm going to do. Okay? I'm going to take this beam, and I'm going to cut a section right here. What does right here mean? I propose that this distance is x. Okay? So I'm cutting a section at some arbitrary location, some distance x away from the left support, right? Because from here to here, that's the x-axis. So I'm going to cut it at some distance x. And I'm going to cut a section and look to the left. Okay, so let me draw that down here. So cut a section at x, look to the left. So what do we got? Here's my beam. Here's my support. I believe we got a reaction here of 10 kips. I believe we have a linearly increasing load. And then here's where we samurai sworded and lightsabered through the beam. Okay? Now, so that we're paying attention, this dimension here is x. Okay? This dimension here is h. Right? what I need is I need to know F and I need to know D. And I need to know those in terms of X, okay? And I'm going to apologize on this, but I'm going to take this H dimension and I'm going to put it over here because I have something I want to put here. What I need to put here are my shear and my moment, because that's ultimately what I'm after. I want to determine that shear and that moment. Now, let's start off with H. Does anybody know how we're going to determine H? How did we do it before? Similar triangles. So H, so hold on. How would we do that? Somebody set that up for me. Is that a fair statement? 2x over 30 or x over 15? So therefore, that, and what is this? If I chug all this out, what am I going to get? X squared over 30. D is what? See, this isn't so bad, right? Hopefully this is pretty straightforward. Now, if that's the case, let's sum forces in the x and y, or in the y direction. So what do I have? I've got 10 going up. What do I have going down? I have V and I have F. But F is this. So I'm going to say I have 10 going up, V x squared over 30. Is that a fair statement? Is everybody okay with that? I don't want to go too fast. So if I scroll a little bit, I'm trying to keep the scrolling to a minimum. So 10 is V plus x squared over 30. I get that. So V is that. Is that a fair statement? Everybody okay with that? All right. Let's keep going. Let's sum moments. Let's sum moments at the cut. Let's take a look at that. What do we got? Well, what do I have? Here's the cut. Does that generate moment? At the cut, does it belong on the left side of the table or the right side of the table? And what's the moment arm? x, 10x. On this side, I have m. I don't need to consider the v because it's going right through the cut. But what about the force? The force times the moment arm of d, right? So the force is that, x squared over 30, times the moment arm of x over 3. Right? Let's see what happens. So 10x equals m plus x squared over 30 times x over 3, x cubed over 90. Is that fair? Everybody okay with that? Help me out. Anybody notice something? What is the derivative of the moment function? What's the derivative of 10x? Minus, what's the derivative of that? So x cubed, the derivative of that? 3x squared over 90 is x squared over 30. So the derivative of this is 10 minus x squared over 30. Passes the derivative test, right? Let's see if it passes the smell test. You're like, what's the smell test? This is the smell test. Let's zoom in a little bit so we can all see what we're doing here. So watch this. How long is this beam? 30. Okay. So here's what I'm going to do. I'm going to put a column here. We'll call it X. Okay? And what we'll do is we'll say 0, 1, 2, 3, 4, 5, 6, 7, all the way to 30, right? So how do you do that in Excel? Maybe start a couple values, 0, 1, 2, and then you highlight those values, right? And remember how you can drag that little square right here. Your cursor turns into a black plus and you just drag it all the way down to 30, right? Right? So there's that. Let's do the shear one first. So let's do V, kip. Okay. Here's my function, right? So watch what I'm going to do. I'll zoom in a little bit so you can kind of see. So equals 10 minus that squared divided by 30. What do you think? All you got to do is the first cell, you hit enter, and then remember this little trick? You put your cursor over the cell, you highlight the cell, and then you go to that little corner and you double click, boom. And you get a bunch of numbers. Do those numbers make sense? Well, what do we get at the bottom? Negative 20. What did our shear diagram look like? I seem to remember that it would start at 10 and go to negative 20. That's just a coincidence. Let's see if it actually looks right. So I'm going to highlight both of these columns of data, go to Insert, and then we go to Scatter Plot, and let's just do this one right here. Scatter plot with straight lines. Zoom out. Well, look at that. That kind of looks like our shear diagram, doesn't it? Now that is a sloppy looking graph. Let's see if we can make that look a little better. So, first off, engineers don't produce graphs without axis titles. So this is we'll say the distance across the beam. This is the shear, right? The beam's only 30 foot long, which, by the way, I'm recording all this, so if you fall behind, don't worry. So let's right-click. Let's format that axis a little bit. Let's change the limits. Instead of 0 to 35, let's do 0 to 30. All right? And then where it says labels here on the bottom, I'm going to take the labels and place them low so that those labels aren't in the graph and I can actually read them a little bit. Then let's give this chart a title, something very creative and unique, like, I don't know, shear diagram. That's starting to look a little bit more like a plot that's respectable. Everybody okay with that? I'll give you a sec on this. Is anybody having any Excel-based questions?
How'd you change range? Where'd you go for that?
So you right-click the axis. Actually, click the axis, like right here, right there. No, dang-nabbit. There you go.
You can click anywhere on the
Right-click, format axis. How are we doing? Is this okay? But have you got the plot?
Yes.
Okay, we'll worry about the formatting stuff later. I just want to make sure generally that you're okay with what we got going on here. Now, I'm not done. I want to draw the moment diagram. Now, what's the moment diagram function? Let's zoom in a little bit. So, equals, right here, 10 times x minus x cubed over 90. I'm probably using more parentheses than are necessary, but parentheses are free. When in doubt, use them. Press enter. Then we use that little double click feature. Boom. Now I'm lazy. Okay, I don't want to redo that plot all over again. So watch what I'm going to do. I'm going to take the entire plot, copy it, and paste it. And then watch this. All I'm going to do is take this little column. See how it's blue? I'm just going to take that column. I don't want to plot that one. I want to plot that one. Boom. There's the moment diagram. All I got to do now is call this moment diagram.
Sorry. I'm trying to get my numbers.
All right, look right here. What? So I copied and pasted the plot again, right? And all I did is see where this column over here on the left is highlighted blue? And see how the cursor kind of has that little arrow with the plus sign? Boop. And then now we call this moment diagram. And change my axis label. Now, let me move these over so that they're a little more lined up. Boom. Let's see your functions. Check your functions. All right, let's see. Well, all right, so 10x, it's minus x cubed over 90. You got x squared. You might want to check your moment function. All right, is this making sense? Now, we're not done. We got to go back to the notebook and do a little bit more math, but everybody kind of following along? Now, look at this. Look at where shear equals 0. It's not at 20, right? It's like at 17 something, right? And then look at the maximum moment. The maximum moment is about like, what, 115, something about like that? Let's see if we can get an exact value on that. And the way that we get the exact value is we go to the math. And before we end, I'm going to show you this approach too. So let's determine where shear equals 0. So this is my expression for shear. Let's set that equal to 0. And let's solve for x. What is the square root of 300? 17.32? I don't know about you, but you ask me, that's kind of where that happened, right? Right? That dimension right there, that's about 17.32 feet, right? Why is that value important? Because if you go to the moment diagram, that's right here. So if I plug in 72.32 feet into this, it will tell me what the maximum moment is, right? So M max occurs at x equals 17.32 feet. So M is 10x minus x cubed over 90. M max is 10 times 17.32. What is M max? Isn't that what the graph shows? So now we have accurate descriptions for our shear and moment diagrams. We know the plots, we know the important values, we know everything we need to know. And before we end, I'm going to show you why plus C matters. Does everybody have this? Now, remember that we said that Wx could be represented by just the height. Remember we said that Wx could just be negative height or negative x over 15. Didn't we say that? So watch this. I propose that v is the integral of that, which is the integral of negative x over 15. What is the integral of negative x over 15? That's right. Negative x squared over 30 plus c. I'm going to call this C1 because we're going to have a C2 here in a little bit. Now, how do I determine that C1? A mathematician would say you need a boundary condition. Well, what is the boundary condition? I propose that at x equals 0, v equals 10. Isn't that what you told me up here? That's what you told me, right? So, what do we got? V equals negative x squared over 30 plus c1. So 10 equals negative 0 squared over 30 plus c1. So 10 equals c1. Or v equals negative x squared over 30 plus 10. Is that the same thing as this? By golly gosh gee, yes it is. And then, if we keep on going, moment is the integral of shear, which is the integral of this. I'm going to rewrite it. 10 minus x squared over 30 dx, which is the integral of 10 is 10x minus 1 over 30 times the integral of x squared. What's the integral of x squared? It's x cubed over 3, right? So this is x cubed over 90 plus c. In this case, plus c2. We need another boundary condition. I propose that at x equals 0, the moment equals 0. That's what you told me, right? So, I scroll down a little bit. M is 10 times x minus x cubed over 90 plus c2. 0 equals 10 times 0 minus 0 cubed over 90 plus c2. 0 equals c2. And m is 10x minus x cubed over 90. If we didn't have our plus c's, this wouldn't have come out right. Plus c matters. What do you think? So your problem on the homework is instead of dealing with a triangular load, it's a uniformly distributed load. So your algebra is going to be a little different. I'll give you an example. It's not x over 3. It's a distributed load, uniformly distributed. So it's x over 2, because it's the centroid of a rectangle, not a triangle. Next time it gets a little better, because we're going to get away from all this crazy algebra and calculus land and get to something a little better, like concentrated moments and cantilevers. That's all I've got, everybody. I'll leave this up for a bit, but I will see you all on Friday.